It's a great pleasure for me to introduce to you Jim Linnemann from Michigan State. He's a retiree, but very active even yet, and a big part of the HAWC Observatory installation, which he's going to tell us about mostly today. Next week, he'll talk more about some of the physics, some of the applications, and some of what gamma rays really are. So I'm looking forward to that. And help me welcome Jim Linnemann.
Are we on? Yeah, good. All right. So the HAWC Observatory. This is a picture. I'm going to actually start off, introduce myself a little bit. Conveniently enough, I retired recently, so there's some slides. And I was given this picture is a framed version of this picture as a gift. This is the HAWC Observatory. And I really enjoy having been part of the construction of the thing. I'm happy to share that information with you. And well, let's get into it. First, I'm going to explain why I'm here today. And then I'm going to try to explain that HAWC Observatory. And I would encourage you to ask questions as we go along. So first I'll say why I'm standing here. Second, why we built this contraption. Then I will try to explain the name and the motivation. And then I'll tell you something about the location which we built the place at. And I'll talk about the construction and some of the sociology that went along with that. And then I'll try to explain the equipment and what it measures and how. I'm not sure I'll get through all of that section. That might sort of, there's a sort of smooth segue between what we're measuring and then what we do with it. So some of it might leak into next week. We'll see. But my goal is that you understand more about this picture than you do now. All right. So I started off as a son of a tenant farmer in rural southern Illinois. Some sociology, which you probably have a good feel for here, is not Dutch surnames, but my town and my county was 90% German surnames. Now, in fact, I think they mostly spoke Flat Deutsch one generation back, so they probably could have talked to your ancestors as well. I went to Cornell University and got a degree in experimental high energy physics in 1978. But I always had interest in astronomy, and includes, there were some very good people there, including Carl Sagan, who was a master communicator. There were a bunch of people who thought, well, I know this silly TV show of his. I think they really underappreciated how good it was at outreach, and they were jealous. I went to Rockefeller University for my postdoctoral work, and that took place at the CERN laboratory, where the LHC is now, on the French-Swiss border. So I got to live there. I wanted to go to Europe. My thesis advisor said, well, where do you want to go next? And I said, I want to go somewhere other than the United States, because I realized it was a possibility in my line of work. And like I said, I grew up in a sort of a small constricted environment, and I wanted to see a bigger world. And luckily, my chosen field allowed me to do that. I've recently started converting some of the big pile of slides of the Alps, and from those years there, I was there 6.5 years. At CERN, so this is, I was a research associate there. Let's see here. This is just the end view of our apparatus. It's a typical smallish high energy physics apparatus, lots of wires. in this case, it's sort of intimately connected to the beams. These are vacuum chambers which carry the beam, and the collisions take place inside of this, and pack it as full of instrumentation as you can and try to analyze it. I was in charge of some of the software, various things, but a lot of the time I was in charge of the software for making tracks, looking how to reconstruct the events in there, and also triggering electronics. Triggering in our context is, well, a lot of things happen. Which one do you actually write out and analyze in detail? This is a picture of us after a group lunch. You notice my beard was a different color then. And, well, can I say? But it was a pleasant life, pretty intense. We often worked 6 days a week, but then there were weekends we took off hiking in the Alps or going skiing. It was a good life. To my astonishment, I wound up, I thought I was going to program computers the rest of my life. But I actually got offered a job teaching physics at Michigan State University. So when I came there, then there's another government laboratory outside of Chicago called Fermilab. And that's where I worked for the next, the bulk of the rest of my career after I went to Michigan State. So that's the apparatus I was working on then. There's more people, and it's a lot bigger and more complicated. So this is what we would call nowadays a medium-sized experiment. One which I spent time briefly on, had 3,000 people signing the papers. In part because of that, I made a transition to astrophysics. Remember, I was always interested in it. And so I took a sabbatical leave at Los Alamos National Laboratory in New Mexico. Astrophysics offered more opportunity for real discoveries. I mean, hydrogen physics was a pretty mature field, so it's actually tough to find something new. And a lot of times what you do is you say, well, I didn't observe something, but I can set a limit on how much it could have been if I would have seen it, which is, I find fascinating, but it's a tough business. Now, during my career in hydrogen physics, I had a lot of experience with electronics, computing, and statistical data analysis, and those techniques translate smoothly into the particle astrophysics that I'll be talking about today. So that's how I was able to move without too much difficulty. I joined something called the Milagro experiment, which was a predecessor of the HAWC thing, which I'm going to be telling you about. And I'm proud to say a couple of things. One is one of my students, an interesting character from Jordan, whose brother, I think, was the religious tutor to the king's children. He found techniques for analyzing the Milagro data, which allowed us to see astrophysical sources that no one had ever seen before. So his thesis title was Discovery of 5 New Sources in TeV of gamma rays. And that allowed us to propose HAWC, right? Because we'd shown that not only the technique works, but you could see new things using it. The other thing is when I came back to Michigan State, I started the particle astrophysics group, which has now actually grown to 5 faculty, not including me, because I'm retired. I will still work on it, but I'm retired. This is what Milagro looks like. That's about a football field sized pond repurposed for something complicated. The red dots are just to show you where there's some extra detectors scattered around in the woods. And so this is a telescope in the same sense that HAWC is a telescope. It's just not obvious. So I'll try to explain how something that looks like that can be used as a telescope. And finally, how did I get to Hope College? Well, actually, another of my graduate students, I came here to visit Peter Gunther in the physics department here because he was doing research which was related to the stuff that my student was working on. So we came out and consulted with him. Then the next step in the chain was, well, actually since 1995, I've been treasurer of Happen Dance, which is a dance company, I think about 48 years old in Lansing. And one of the things you have to do when you're treasurer is participate in fundraising. You know how that goes. So I was selling poker chips. And one of the people I was selling poker chips was none other than Patty Villanueva, Gordon's daughter. She, by the way, was my daughter's ballet teacher. So Patty was a Hope graduate. That's where she got her degree in dance from. And well, now he's explained to you the last little steps in the way. So here's why I'm here. I'll say just something which I tell all of my graduate students. Doing the kind of research that I've done is too hard unless you have passion for it. If it's just a job, it's too hard. But if you're excited to wake up each day and be able to do it, that makes it possible to do. And I am well aware that you guys' taxes have gone into this because it takes money. And I really enjoy the fact that my physics has allowed me to travel, work with people from all over the world. It's a good life. So I want to share some of that joy with you. Now, I have a question for you. Just, how many people have a science background? I'm just curious. Okay. Well, there's a certain selection by the topic you chose, right? So that crew at least is not going to be too frightened if I use exponents 10 to the something. Okay. How many are interested in astronomy? Okay. And this is a funny mixture between physics and astronomy. Physics techniques, physics underlying the analysis, but astronomy as the subject which we're studying. Anybody else have any just comments about why they're here? Okay, back to HAWC. So that's that picture. I want to try to explain what you're looking at. Why did we build it? So the point of scientific instrumentation is to extend our senses. If you get a little forward, you can say it's extrasensory perception. And when you build a new kind of instrument, you can see things you could not see or even imagine before. Classic examples are Galileo's telescope, seeing the moons of Jupiter, or Van Leeuwenhoek's, a good Dutchman, use of the microscope and finding all kinds of things that were smaller than our eyes could see without assistance. So HAWC is a telescope that is dedicated to TeV gamma rays. And I'll explain a little later what TeV means. Now, I have to say it's a pretty weird looking telescope, but the reason it looks so different is it is not, telescopes you're used to are built to focus light. And we don't do that. We make images rather differently. I'd say that HAWC is an example of extreme astronomy. We look at very different kinds of light than what you're used to seeing with just the Hubble Space Telescope or the Webb Space Telescope, much, much higher energy. And in fact, only really exotic sources produce the kind of light that we can see. So photons, which are particles of light, and I'll say a little more about that later, a gamma ray is a very high energy photon. And all light comes in quanta called photons, including the light from the sun. It's just that there are untold trillions of them, right? But the individual energy of one of them is quite small. In fact, we are looking at light that per photon is 1 trillion times higher energy than the light that comes from the sun. So the sun basically doesn't produce any such light. We're looking for things other than the sun. Now, the idea of the photon is that a different wavelength corresponds to a different energy. So the wavelengths that we can see well, it's red to bluish, to a little bit towards the indigo, right? Beyond that is ultraviolet. That's the territory where the energy gets higher and higher. And gamma rays are beyond those. They're beyond X-rays, and gamma ray is everything to higher, as high as we can measure. It doesn't have the wavelengths bands written split up as much. Now, we don't normally notice that light comes in quanta because there's so many of them. But our eyes are not too shabby. In fact, if you spend enough time outdoors and somebody lights a match 10 miles away and is standing in a place where you can see them, you can observe them, but that your eye is actually observing one or two individual photons when it does that. So there's quantum processes going on inside your eye, which allows it to do that. But most of the time, there's so much light, we don't need to be so sophisticated in the processing of light. Now there's a problem for wanting to observe TeV photons, and that is that our atmosphere absorbs them. So how do I observe them anyway, in spite of the fact that the atmosphere has absorbed the thing before it comes to me? I'll explain that. And HAWC, my relationship to HAWC is after my sabbatical yes, 10 to the a trillion electron volts, tera electron volts. Yeah, thanks. So we held the first meeting about HAWC in 2004. We actually had the thing constructed and had an inauguration ceremony in 2015, so over a decade later. We have to do long-range planning for something this complicated. And I was in charge of the electronics and heavily involved in the remote monitoring. It's on a mountaintop. It's a pain in the neck to go there. It gives me a headache whenever I go there. And so you want to do the monitoring and make sure things are okay. You want to do it remotely from your office. I mentioned that it takes exotic sources to produce these very high energy gamma rays. Here's some examples. Most galaxies have enormous black holes in the middle of them, but some of them, the black holes actively dining. They're very sloppy eaters. And the part that doesn't go into the black hole often produces a very high energy jet. Okay. And by the way, if that high energy jet is pointing right at you, it's incredibly bright. So the three brightest things that we see in our sky, the brightest is the Crab Nebula, which blew up in 1054 AD. The second brightest and the third brightest are two different galaxies, but that are in this Blazar class, which point right at us. So those jets of particles are things which we can observe. The Crab Nebula, which I mentioned, has a neutron star left over from the supernova explosion which happened. And that also is a mechanism for accelerating things to extremely high energies. Other things that can happen with supernovae is the fragments of the supernova can be scattered around near where the star was. And cosmic rays, which I'll talk about a little bit later, can run into it, cause interactions, and also produce very high energy because some cosmic rays are very high energy. You can do that kind of thing. More exotic things still. There can be collapses of black holes, stars into black holes at the stellar level. And we've been starting to observe things related to two black holes running into each other. So all of those are exotic enough that they can produce things that are high enough energy for us to see. But most stars we can't see. They're just not emitting in that range. So here's a little bit of a lay of the land. This is a graph which on the vertical axis is showing you how many per second particles hit the Earth. And on the horizontal axis, on the log scale, is the energy where the energy down here is about 1,000th of a TeV, 10 to the 9th electron volts, and it goes up to around 10 to the 20th or so, which is the highest that anybody's seen on Earth. Again, there are enormous detectors covering many, many square miles, much bigger than HAWC, which are looking for those kind of things. And the reason they build them so big is because these are extremely rare. Up in this energy range, there's 1 particle per square kilometer per year. Tough business. So what do we want to know about these guys is we'd like to know what produces them and what are the processes going on. We're sort of curious whether there's any new physics which might be going on at the very end of this. But most cosmic rays are charged particles. Photons are special because they're neutral and they point back to their source. We can do astronomy with them. Charged particles are too messed up and they've forgotten where they came from. The low energy cosmic rays come to us from the sun. The ones up to, say, this area, which is generously called the knee, where there's a little bit of a kink in the spectrum, probably coming from somewhere in the galaxy, probably related to supernovae. We wonder about what the sources are. Extragalactic stuff, like those dining black holes, those are things you don't want to be too close to. So it's okay with me if they're in another galaxy rather than ours, getting overexcited now. And the way we try to answer some of these questions is, well, first you have to collect data. You have to go and measure sources. You figure out where they are in the sky. You look at what other wavelengths, what other observations people done, what kind of thing they might be. In the entire TeV catalog, there's a website devoted to that. When I looked yesterday, we're 275 entries. There's a lot more stars than that, aren't there? So this is really pretty exotic stuff, and we're trying to understand. Now, the cosmic rays, a little over a century ago, people didn't know that they even existed. They had to convince themselves of that first. So this guy did a balloon flight with a scientific instrument at the time called an electrometer, and he took it above, up to, I think, was it? Yeah, around six kilometers, I think he was on. And what he saw is a funny thing. There was a rate at the surface of the Earth. When he went up into the sky, the rate dropped. And then and that's sort of consistent with the theory of the time was, well, these guys must be coming from stuff on the Earth, like uranium ore, for example, right? But when he went further up into the sky, the rate started climbing again. That means there was another source which wasn't on the Earth, but from the cosmos somewhere. As I mentioned, the charged cosmic rays can wandering off all kinds of funny directions. That's because there's magnetic fields out in the universe, and so they bend their paths. Charged particles don't go in straight lines when you have magnetic fields. On the other hand, gamma rays, neutrinos, and actually gravitational waves do travel in straight lines, and you can do astronomy with them if you can manage to observe them. Takes some effort to observe them, but you can. Now, I mentioned that HAWC is a very peculiar looking telescope. Here's one which you may feel more comfortable with, right? That looks like a telescope. It is designed sort of on classical principles. It can do measurements. I'm not going to explain how, in the same kind of energy range as we are. Here's the Milagro observatory I talked about. And there's another one which goes in slightly lower energies than us, called the Fermi-Lat satellite. That's a satellite flying up or outside the Earth's atmosphere. But again, these are all measuring very high energy gamma rays with rather different techniques. So the techniques govern what the thing looks like. Now, about the name HAWC. You will notice that we have a bird in our logo, right? It's not that we can't spell. I get, some people could say it depends on how much you're willing to torture the letters to make an acronym, right? There is a K in Cherenkov, so we could have spelled it right, but no. I once was collaborating on a research proposal, which I counted. I think I had to correct the spelling of HAWC back to HAWC something like 64 times. Because after all, spell check was helping us, right? So what the HAWC is an acronym, it stands for High-Altitude Water Cherenkov. And I'll try to motivate that name next. Now, if you go Google HAWC, you will find the Houston Area Women's Center, Hellenic American Women's Council, and also another scientific instrument, the High-Altitude Airborne Wideband Camera, or SOFIA. I claim at least our acronym is less tortured than that one. So why high altitude for TeV photons? Because, as I said, they're observed in the atmosphere. They're absorbed in the atmosphere. So since you can't absorb them, directly, and they're absorbed in the atmosphere, in fact, there is something else which we observe, which is secondary products of that. And unfortunately, those too are absorbed in the atmosphere. And so the general principle is if we go up higher in the atmosphere, less absorptions happen, we have something to measure. And that's why we go to high altitude. Here's sort of a picture of what happens when I say the thing is absorbed. About 20 kilometers up in the atmosphere, TeV photons hit some nucleus of some atom and produce other stuff. In fact, they can produce thousands, even millions of particles. They're part of the cosmic ray rate. A small part, but they are, right? And here I'll do a little physics. I'm sorry, I'm a physics professor. I can't help myself. Right? So here's E equals mc squared equation, you know. I have a lot of energy. That means that I can make a lot of mass. And what I'm doing in this diagram here is I'm actually creating electron and anti-electron pairs by the millions, right? So I take the 10 to the 14th electron volts, that's the 10 to the 12th electron volts is a TeV. So this is 100 TeV photon or gamma ray, and I can produce millions of electrons. Each electron has a half of a million electron volts in mass. So a pair is 1 electron, million of them. So a TeV could produce about a million electrons, but then it wouldn't have any energy left. In fact, these guys have a lot of energy left. So I'm drawing you 100 TeV photon, and it can produce millions of electrons. And some of them come down to the Earth, so we can have a chance to observe. Now, and as I mentioned, the typical photon from the sun, which we use for revision, is maybe 1 electron volt. Electron volt is the energy that one miserable little electron gets going through the battery in your cell phone, right? And it's also a typical energy for example, any chemistry reaction you've ever heard about is around an electron volt. It's a tiny amount of energy, right? But this, what happens is I am somehow getting many trillions of times that amount of energy invested in one photon, and that's what I'm trying to. That's exotic phenomenon I'm trying to observe. So if you make a plot of how many particles there are in one of these showers as a function of depth, well, you're a lot better off if you're not at ground level when everything's been absorbed. And so we settled on 4,100 meters. 2,800 meters or so was where Milagro was. And it was a harder experiment to run there because you had less to work with. So we went up to high altitude, and this is the before picture of HAWC in 2009. The second part of the name is Water Cherenkov. Okay, why water Cherenkov? Water is the medium which we use for detecting the particles in those air showers, which I'll explain how. And an air shower, what goes on is an air shower goes through the water. It's traveling more or less at the speed of light. And by that process, again, I'll give you some hint of, it produces Cherenkov radiation. Cherenkov is the name of the Russian guy who figured out the theory for this. He won a Nobel Prize for it. We physicists can't help ourselves always bragging about the guys who won Nobel Prizes. But we detect these Cherenkov photons with things called photomultiplier tubes, which I'll explain a bit about later. And so that's sort of the sensor of the transducer. And we put them in a place where there's no other light. We produce tanks of water with the light, all external light removed, and therefore the light that happens is just that Cherenkov light. And so they can detect the Cherenkov light and see that something has been come through the water. This, in fact, is the same basic technique as in the Malagra thing. And anybody speak French? You get this joke? You get this joke? So I would argue that given its constraints, HAWC is a highly sensible detector. I remember seeing a research proposal at CERN where somebody proposed a highly sensible detector. And actually what they meant was a highly sensitive detector. Those are called faux amis, words which look like they're the same and they're not. So they bite you. Okay, a little bit about a Cherenkov radiation. The basic idea is it's a shock wave. In this case, it's an electromagnetic shock wave, but it's an analog of a sonic boom. Why does a sonic boom happen? Because the plane is going through the atmosphere faster than sound waves can propagate. And they make a cone like this. And so as you sort of watch, let's see. Whoop. Let me go back. There we go. And as the particle moves in this direction, at each point, it sort of radiates and they line up along these planes, and that's the shock front. So the same thing happens in water when a cosmic ray or a particle in those air showers go through the water faster than the light can propagate in water. In water, in fact, the speed of light propagation is only about 3/4 what it is in the air or the vacuum. So it produces that. This unearthly glow here is a picture taken of a research nuclear reactor at, I believe, at the University of Maryland. It produces Cherenkov radiation. Cherenkov radiation is in the blue to the ultraviolet. We can't see the ultraviolet, but you can see the blue. So that's what we have detectors to do to check for. So the basic scheme is we're going to have showers coming down. We're going to have an array of detectors. Each of those detectors is going to be a huge water tank. And the purpose of the water is to make Cherenkov light. And in each water tank, we have 4 phototubes to detect that light. Now, why do we build it there? Where it is near, in high altitude, you need mountains. One way to get mountains is to have volcanic activity. And there was a big volcano behind HAWC. In fact, that's the highest mountain in North America outside of Alaska. It's over 18,000 feet. Easily the highest mountain in Mexico. We're not on the top of it. We're in the swale between 2 of them. And the neighbor mountain to that is here. It's called Sierra Negra. And there is a radio telescope, 50 meters diameter dish, on that mountain. HAWC is between the 2. It's down here. Here's an airplane view. This is the Setlapetl, which is Nahuatl for Star Mountain. also called Pico de Orizaba. And then Sierra Negra is the other mountain with the radio telescope on top of it. And yeah, that's another volcano near Puebla, Mexico. So our site is between the two mountains on a relatively flat area. We had to get heavy equipment to actually make it close to flat. Now, that radar telescope is a big deal for us because it got there before us. This is not a big surprise. It's a national park, highest mountain in Mexico. But they had gotten the permits to build that radio telescope in the park. And in order to make something useful out of it, they had to build a road up the mountain, run power lines, and run internet fibers. So we piggybacked off that. This is one of the things that made the site special. Now, we considered other sites. We considered a site in the US. There's a research center on a mountain at good appropriate altitude in California. There was no way we were going to get permits for accessing the water, putting the water at the site, and building all that stuff. We considered Tibet, where there's other experiments parallel to the kind of thing we were doing. The infrastructure was all there. There was that running water. There was a river. Tibet is so ridiculously high that a 4,000 meter high valley has mountains that are taller and around it, and water running down. But it's really a pain in the neck to access from the US. It's probably 2 or 3 days to get there. We considered some other sites also in Mexico, but they had less infrastructure. That's where we wound up there. So that's our site, and we like it. Now, there are consequences. I wanted to be at high altitude, right? That's 13,500. You only have left 60% of the atmosphere, right? 40% less atmosphere that you have than you have at sea level. Among the peculiar things that happen is that laptops are spec'd to live at about 10,000 feet maximum. And if you have disks, well, it turns out the way that platter rotating disks work is they spin and the heads or the detectors float on air. If you don't have as much air, you have a problem. So we often had to use before it was less as common as it is now, we use solid state disks. Oxygen deprivation affects humans. I am fairly susceptible to this. I start noticing it in Denver. For 13.5, I don't work very well. When we went first to check the place out, we walked around there. Oh, yeah, this is, well, okay, yeah, all right. And then we got into a van and drove another 1,500 feet up to the large Magellanic, millimeter telescope. And I remember saying, well, I'm really glad that I'm down there, not up here. That last 1,500 feet was really quite noticeable. And people can get altitude sickness, right? It's a concern. So I argued that we should have oxygen enhancement, at least in the control room, right? I lost that argument. It would have cost as much as one more detector. 1/300th of the budget, guys, come on. No, we can't do this. There was a secondary meeting. It's fantastic. People make apparatus which take air in and say, okay, I tell you what, I'm going to shoot the nitrogen out the left hose and oxygen out the right hose, right? So that's just what we want. But then you have to mix it back into the air correctly and not burn up anything and so on and so on. So there's some technical problems in doing it as well. So we didn't. So examples of stupid, two of the senior distinguished members of our collaboration once spent an entire hour arguing about where to plug one cable into a high voltage supply, which they had both used at lower altitude many times. And my personal favorite, the astronomers, when we told them that we weren't going to, we're going to be real minimal to this, yeah. And not have oxygen enhanced sampling. They said, you're idiots, and started telling me stories about how they operate. Mauna Kea is somewhat higher than our site. Big telescope there. Their way of operating is at sea level, you write down what you're going to do. You drive up to the site and you execute the plan. If something goes wrong, you drive back down. There are reasons for that, bitter experience. One well-known astronomer forgot to push go and wasted an entire night of astronomy. And my favorite was a technician who had been working on something. This is before they developed the proper plan. He called down and says, David, I've cut this time pipe 4 times and it's still too short. So oxygen deprivation is the thing. And this is another of the reasons which I like this site. You can drive down to the valley at 2,700 meters, ain't nothing. But in 45 minutes, you can gain 1,400 meters of altitude. That's enough to cure most people of altitude sickness. In Tibet, you have a 2-hour drive to get down to 3,700 meters. And if that isn't enough, they have to airlift you. And one of our colleagues was in a site prospecting visit when one of these scientists, Chinese scientists, had to get airlifted. It gets your attention. Okay, how do we build HAWC? So Milagro, if I look inside that canvas thing, is an open pond with lots and lots of phototubes. You can't see it because the water is quite clear, but these are 4 meters underwater. We use modular tanks, and we're much happier with this. It shields the phototubes from each other, so each is measuring something that's distinct. It allows us to build incrementally. You can build the first 6 tanks and see how things go. Practice the assembly, practice the installation, and you can test and see if things are working right. So the structure of one of those tanks is there's the outside stainless steel water tank. Inside is a waterproof and light-proof liner. Then there's a dome, actually just fabric and a space frame, which I'll talk to you about later. And then inside is a lot of water, 20,000 liters each. That, it's 50,000 gallons, give or take, per detector, per water Cherenkov detector. And then, if you imagine a particle going through there, well, it goes through and makes this Cherenkov light, and those detectors, the photosensors down at the bottom, are there to measure the light. We have to survey everything. We know where each one is to within a few millimeters. That allows us to analyze the data. Now, we originally considered trying to build really big plastic tanks, but that was impractical for several ways. We spent 6 months measuring the height of all the bridges on the highway we'd have to go past, see whether we could get under them, even with low boy trailers. This is much more civilized. They come on a flatbed, and there's the pieces, right? Just snap them together like a Lego, right? So that's what we're aiming at. But in fact, we took a design which existed in California for storing water, which is great because it was earthquake certified. They'd really they understood the engineering, how stable the thing was. That was required of us. There's earthquakes in Mexico. But those guys at one site assemble 1 or 2 tanks. It's just like, I had a couple of tanks that look an awful lot like this on the farm that I grew up for holding wheat. And they're pretty good size. They're maybe 24, 25 feet in diameter, 15 feet high. You're sort of pain in the neck to assemble. You don't really want to be climbing up and down ladders. Remember, even the guys who are doing this, who grew up down 2,700 meters in the valley, they're still affected by the altitude. And you don't want people to hurt themselves. So what we wound up with is this. You dig a trench, you put jacks down there, you assemble one ring, and then you jack it up. And then you assemble another ring at ground level, no ladders, right? Snap it on, jack it up, put on the next one. So we never have to go climbing all the ladders, and nobody got hurt building. Inside of these huge ladders, they were built in Colorado. And then here are what physically those phototubes detectors look like. They're pretty big, right? Made in Japan. And then, well, there isn't a big hose at the top of the mountain. So we had water tankers driving up the area. That was, by the way, a large fraction of the expense of building the thing, just hauling the water up from the valley. We also had to purify it, but that costs nothing compared to the trucks running up and down. It's a lot of water. There's enough water in our apparatus to give everybody in Mexico a bottle full of it. And when we moved the bladders from Colorado, shipped them, interesting international customs operation, to Mexico, well, then we had to reinflate them and make sure they were okay. Because, by the way, these have to be light tight, right? So no little pinholes, or else go fix them. So, and the tankers have right of way. It's a mountain road, right? If you're going up to the site in your four-wheel drive vehicle, which you need, the road gets a little bumpy, and you see the dust coming from one of these guys, you have to find a place to pull off because they have the right of way. There were almost 4,000 tanker trips. Fill this thing up. 300 tanks. It's fair enough to ask how much of all this cost. The assembly was basically a little under 10 million bucks. It was completed on time and on budget. We're pretty proud of that. 10, 15 million, 7 million from the National Science Foundation, which is the agency that funds my work, the Department of Energy, which funds Los Alamos, and 4.5 million from Mexico. There are also these extra detectors called outriggers, which I'll say maybe just a little bit about. It operates nowadays with remote operation. It operates 90, 95% of the time it's running. It still costs another couple $1 million a year to pay the crews and do the various miscellaneous things that were required to keep the thing running it and doing an apparatus. It's big. You can't really tell the scale before. So this is 150 meters, so well over a football field on the side. So here's some trucks. In the middle is where electronics is. And here's where the utility is, for example, the water filtration plant. And the outriggers are decorated all over the place. You see, this is the area where you can see the grading, right? This is the area we flattened. And then the outriggers said, well, okay, it's not so unflat here. Haul the suckers out there and put them down. And they are of different heights. There's 350 of those, which we are running. They're taking data, but we actually have not finished the software to incorporate them. That was sort of a tough business. Let me tell you some stories. We're in a national lab, right? A national forest. There was what we would call politely an informal logging operation. This is actually the highest, I think it's the highest pine forest in the world, up to 4,000 meters. And we offered to let people know if we saw something funny going on. That was not well received. because guess what? Some of the locals were involved in the farm logging operation, including apparently the mayor's brother. Elections. So in Mexico, a larger fraction of the bureaucrats and commissioners are replaced when there's an election. And we had, at some point, partway through the construction, there was an election, and a completely new set of perks people were elected. And it was almost like we had to renegotiate the contracts from scratch. The water contract, to the you mentioned a lot of the money, right? Was won by, guess who? The mayor. Yeah. There's as you drive up to the site, you go past a nice road leading to a rather nice house, just sort of above the level of the town. And we tell all students when they join us, is, you see that road? That's not a road. Or more precisely, that's not a government road. You do not drive on that road. It is used for other purposes. I'll let you guess. We went through a couple of lockdowns, one because of COVID, one because related to the cause of the not a road. Some of the drug gangs in Mexico decided that it was actually a better gig stealing money, stealing gasoline from gasoline pipelines and selling it to the government-owned gas stations than selling drugs. Now, you can't go down to your local hardware store and get tools to tap into a gas pipeline. You have to have bribed Pemex engineers. And two gangs got into it about who had the rights. Many unpleasant things happened. Somebody from the telescope got kidnapped. They chucked him out once they'd stolen the van, the observatory van. And one fine day, some state police from the town, from the state capital, came to the little town for the mountain, and were trying to arrest somebody. And well, they were outgunned. So they were kidnapped and hauled down to Veracruz on the coast, where they were executed. And shortly after that, the state police arrived in force and arrested the mayor, the entire town council, and the entire town police station, police force. And for basically a year and a half after that, even our daily crew going up from the town went up with the police escort if they were going to go up. It's a different, it would have been different problems if we had been in California. On the other hand, there's some interesting things, right? So this is the most visible science project in Mexico, and they're proud of it, and they should be. At the inauguration, there was a national, on the biggest network, there was a 4-part TV special, and there was tens of millions of viewers, right? A lot of outreach work done by the universities in Mexico. So different things happen. And we had another election recently, 3 or 4 years ago, I guess. There was a new science commissioner. Remember, we got $4.5 million from the Mexican science government. Well, they thought that was sort of a waste of money. We want more practical science. So we're anxiously awaiting the next election and see how that goes. But we have not had a general collaboration meeting in the United States because of that, because our Mexican colleagues, if they can drive to the collaboration meetings, that's fine. But if they need to fly, they don't have money. So, yeah. So here's the array. Here's a mild winter scene. we've had worse. Remote operation on a mountaintop can be pretty tough. The crew comes up daily. We've survived a direct hit from a hurricane coming off the Gulf. It tore the anemometer off the weather station. I think it topped out at 110 or something miles an hour. We have a lightning detector for reasons I'll explain in a moment. We're exposed up there, right? But the lightning detector didn't work. And we found out that what we had to do was we had to heat it so that the innards involves something spinning, right? And the innards have to be heated so that they don't freeze up. Something snagged about 100 meters of our internet fiber one time. We weren't able to send data down the hill for about a year. No, about six weeks, a year or two ago. The environment up there is quite variable. Sometimes it's so dry that you have to be really careful when handling electronics so you don't zap it. And at the other extreme, you can leave a toolbox sitting out overnight. And when you come back, it's been so humid that it's full of water, literally, just condensed on all the iron tools. We have all those phototubes have electronics sealed onto them. And unfortunately, we've had several instances where components have failed. So we're sort of continuously replacing them. And we've had a couple of insurance incidents. The laboratory, national lab, which supervises the site, luckily got insurance for everything, right? So for example, a much bigger snowfall caved in some of the space frames. We had to replace them. There was a fire, which, remember those outriggers? There's electronics cables running to all of them. About a third of them got burned. Grass fire, just a little grass fire. We had lightning damage to some of our electronics. That was our fault because the grounding inside wasn't good enough. Well, we learned from it. We haven't had problems since. And we've repeatedly had damage to the transformers, which come from the electric line that comes up. Well, it's going up a mountain. It can get hit by lightning. And it's a tough problem to avoid that happening again. Now, I'm going to show you a little bit how we relate to cosmic sources. So this is sort of a loop. You start from whatever cosmic object produces this thing. And around that is always dust and gas and other forms of light from other stars. So if I'm going to produce a TeV photon, how does it get to us? Well, sometimes it'll run into the protons or photons. They run into other, let's say, hydrogen gas around there, in which case, then it can produce a hail of particles, some of which are so-called pi zeros, neutral pions, and those particles can decay into pairs of photons. And so that's something which we can observe. We observe this is produced at high enough energy, then these light particles coming through can be produced and we can observe them. Another thing we can happen is, like say, for example, near a neutron star, you produce really high energy electrons, but there's magnetic fields around, or they go past nuclei and they get bent. And when they get bent, they can radiate. So if these are high enough energy electrons, then even the radiated photons we can observe. The electrons can also be cruising around in the magnetic fields around there, and the curvature of their path in the magnetic fields can also radiate very high energy photons, which we can observe. And here's a fun one. Let's say you have light with just a few electron volts of energy radiated by some star, right? But if it's near one of these very high energy electrons, it runs into it, it has a collision, and it can boost that photon up to an enormous energy. We can observe it. So those are some ways that we get photons which we can observe. So now you have gamma ray photons. Now they get to the Earth and hit the atmosphere. So what happens is that there's an initial interaction, and a typical thing that happens is that photon produces, as I mentioned earlier, an electron, positron, and electron, anti-electron pair. And then those run into something and radiate another photon, not as high as the initial one, of course. And then that one can produce another set of electron pairs, and so on and so on and so on. That's this mechanism which takes one very high energy particle into lots and lots of lower energy particles. So that's the air shower cascade I talked about. Now, that cascade in the air produces a bunch of secondary particles. There's a roughly plane or somewhat plane, curved plane about when the earliest ones of this thing arrive. So we call that the shower plane, the sort of the leading edge of these particles coming down. And we're going to try to observe that. And the way we're going to do that is we're going to run them into the water in the detector, and that's that Cherenkov light. So the water tank produces the Cherenkov photons, and we observe them with the photomultiplier tube. I'll show you a little bit about what's in the photomultiplier tube. So here's one of those photomultiplier tubes. Here's something of what's inside of it. The inside of the Cherenkov light, in the water tank, the Cherenkov light comes and it hits this phototube. Painted on the inside of that phototube is a so-called photocathode, which is specially chosen material where the light comes in, the Cherenkov light comes in, and it kicks an electron out the photocathode. The inside of this thing is evacuated. It's basically vacuum, right? So now you have the electron that's running around, and then you place electric fields through various pieces of metal inside the thing, so that if it hits this piece of metal, then it kicks out another electron, maybe a couple of electrons, and now you do this a number of times. So each these are called dinodes. Each dinode, you take one electron in, you put a couple of electrons out. There's an electric field designed so that it accelerates these guys from here to here. These guys that are here see another attractive electron field here, and they get a bunch of kinetic energy and smash into the next one. So one after the other, you get more and more and more of them. So you multiply the number of electrons up to amount that you're actually big enough to detect with electronics. Now I can't help but mentioning Einstein again, okay? So the photomultiplier tube, the whole principle is based on a quantum mechanical effect called the photoelectric effect. And this is one of the things which forced people to recognize that photons are particles of light. Now, you also know that there are different wavelengths, right? And one of the confusing things about quantum mechanics is that particles of light have both the characteristics of particles and the characteristics of waves. When we concentrate on one aspect of them, by, for example, seeing whether I can produce an electron by shining some light on the photocathode, I'm going to emphasize the particle-like aspect. It depends on this equation, which Einstein developed, which says that the energy of a photon depends on some constants and inversely proportional to the wavelength of light. Short wavelengths of light are more blue or ultraviolet, so small wavelengths mean large energies, and correspondingly high energies mean very short wavelengths. So if I'm going to make a TeV photon, the wavelength is incredibly tiny, right? Not something that you're going to be able to observe. The energy that's produced, if this is an electron, if this is one of the Cherenkov photons, has to be big enough to remove it from the photocathode. And the photocathode is deposited on the inner surface of this phototube. That's that gold colored coating. And that series of electrodes inside of the photomultiplier is what multiplies one electron produced initially up to maybe 10 to the 7th or so, which we could observe in electronics. Now, Einstein actually developed the theory of the photoelectric effect in 1905. He was awarded the Nobel Prize for this, not the other things you heard about, in 1921, because they were still a little too controversial. In the same year as the photoelectric effect, he also developed special relativity, which we use at every step of the analysis of the data. And in 1915, he developed general relativity, which is necessary for understanding things like black holes. But as I'll mention later, we use general relativity in order for the HAWC apparatus to work properly. So we use all of those things from Einstein over a century later are absolutely integral to how our apparatus works. Okay, so next step, after you have multiplied up the signal to a measurable level, is you have to put it in the electronics. This is sort of a fisheye view of our electronics cabinet. So there's like 10, 12 racks of electronics to analyze this. Here's a slightly better picture of it. And that all lives in this central building. It's in the center so that the amount of cable that goes there is minimized. Over here is a utility building, one with the pickups sitting near it, and that's where the water filtering plant is. Now, here's a picture of one of the electronics cards, which is used to analyze the signal that comes out of the photomultiplier tube. There's 300 tanks, each have 4 tubes, so 1,200 photomultiplier tubes. And there's some things, I think they're probably over here, the so-called front-end boards, which take the signals and amplify them up to a larger level. In this apparatus is handles 64 channels, so we have a whole bunch of them. We measure the time at which the signal arrives. We measure it to within a nanosecond. A nanosecond is a billionth of a second. We also measure the duration or the height of the signal to say how many Cherenkov photons actually hit the phototube. And we're also using that in the analysis. So our raw data is for each PMT, a time of arrival and an estimate of the number of photons that hit. So the physical chain is original TeV photon, air shower into lower energy particles, them hitting water and turning into ultraviolet photons in the water, the photomultiplier tube, measuring them. And then, so we measure the UV photons, and then we're trying to infer from that the original TeV photon. I'll spare you the calibration that goes into it. It's a lot of work. It's unglorious, but if you don't do it, you don't have anything. I'll just say. So postdocs at work, right? The event processing is we say, look, I want for something to be worthwhile to measure, we would require 30 of those phototubes to have gone off within a pretty short time of each other. Okay? And then we regroup all the data for a larger time distance around one of those clusters and record those. So that we call an event. An event for us is the arrival of one of these cascades. And those happen at 25,000 times a second. Unfortunately, most of them are cosmic rays, charged cosmic rays, which are very hard to use to do physics. So we have to dig out the photons from them. I'll probably talk about that next week. We store all the data on disk. We run reconstruction algorithms, and I'll say a little bit about what's going on there. And that takes about a few milliseconds per event. One computer can't keep up with this. So we have a collection of computers. We farm out, here, you work on that set of events, you work on this set of events, and we'll write down the results. Each event comes with a timestamp when it happened. In order to have a solid time base for that, we use GPS satellite information. And as I sort of implied earlier, the GPS time satellites orbit the Earth. They are not at the surface of the Earth. One difference with things that are sitting on the top at the side of the Earth is they live in a less intense gravitational field. Therefore, they have less energy. General relativity tells you that clocks run at different speeds in different intensity of gravitational fields. And so your GPS, the GPS that told us turn left here today, right? It doesn't work unless built into every one of them are corrections derived from Einstein's general relativity to make it work. So we're using Einstein's general relativity even just to run the apparatus, not just to analyze the physics results. All of that happens in the counting house. And then we also plot sort of preliminary results from the preliminary reconstruction. Those are reviewed by physicists at their home institute. I was on shift on Monday looking at provisional results, saying, okay, yeah, it looks like things are still healthy. Okay, the events are all about the right same size. All the high voltage is on. Okay, well, the weather is not so bad. Okay, all right, so probably no problem there. And you look at the currents that are drawn by the piece of the apparatus. You look at the temperature of the electronics, because if the temperature is too hot, things are either going to get into trouble or something got out of calibration. So you have to be monitoring all this stuff remotely. You were going to ask something. Sure. Yes. And I've been instructed to repeat your question. Okay.
Sorry,
Yeah, go.
I know better. So on that site, you have X number of those photo multiplier.
About
tubes?
1,200.
1,200.
Yeah.
So during an event, do all of those detect the same event?
No, sometimes all of them will go off. That's when we have an enormous shower.
Right.
Most of the time, a smaller
So
number.
you'll
do.
see some segment, some
Yeah.
portion of
Yeah,
that picking
yeah.
up the data.
Yeah.
Okay.
And the
Um,
software is supposed to figure out
and that's
from that.
and that happens in milliseconds or
Yeah.
nanoseconds, or some
Milliseconds.
really small number.
Milliseconds, yeah. Yeah.
Those are both about the same in my thinking. They're not in yours, obviously.
Yeah, yeah.
Thank you.
Nanoseconds is for electronics. Milliseconds is okay for computers. We have to write software carefully, and that's done by graduate students and postdocs. We use C++, which is a relatively efficient language, which is sort of obnoxious to work with because it is always checking you. Well, but what kind of an integer did you mean this to be? But that prevents you from making certain classes of mistakes. And it allows the code to execute efficiently, which is important.
Okay, so one more. Earlier, you mentioned estimating.
Yeah.
It was probably on a slide or two ahead of this. Doesn't matter. I'm curious about mathematically what that means. And I'm
Okay.
not a mathematician, but
Yeah,
you
yeah.
say an estimate, it's plus or minus or something
Yeah.
like that. Can you give us an order of magnitude or how you go
Okay.
about arriving at that?
Yeah, I think I'll probably talk some more about it next time, but I'll just mention here. So we are able to reconstruct the direction from which that original TeV photon came, depending on how many of the detectors went off, right? More detectors, more information, better angle, but we can reconstruct to maybe 1/10 of a degree the angle, which is, crappy by optical standards, but, you know, again, I'm only looking for fairly exotic things. So I'm not, is not trying to compare it to every star in the sky. So we can do some reasonable association of where it might have been coming from. And the energy can be estimated somewhere, 30% or worse for low energy ones, and maybe down as low as 15% for high energy ones. And that's to me an astonishing feat. But I pressed one of my graduate students who's now working for Google really hard to use neural networks to do that reconstruction. So we're not as cutting edge as the LHC experiments, which have 3,000 people working for them. We have like 100, but it's not Chubb Liver either. Yeah. Now I'll talk some more about that process because, yeah, you saw what the raw data is. It's sort of little grunts and oofs, right? And to go from that to say, well, astrophysical object right there, not, it's a big leap, right? It's hard. Yeah. So as I mentioned, the physicists write all the reconstructed and analysis program. And when they leave us, they're trained at a level to be professional data scientists, which many of them do. My student, I don't know what he does anymore. Right. But you know, he got he was asking good questions on the networks, and they sent him an invitation. And then as well, why don't you prep by reminding yourself of your undergraduate computer science before you interview? And he went through 3 levels of interviews, and well, they offered him a job. So he's in California now. So we've always in our field prided ourselves on leaving students with strong technical skills, which, you know, yes, they've written a PhD thesis before they leave us, so they have to be sophisticated science analysts, but they also leave with marketable technical skills. The field in general has insisted on high-level computing. We work in a pretty demanding environment, so that can be translated different ways. And nowadays, I mean, some of them, one's a beastmaster. He runs a farm of hundreds of computers for some company. Mine is working inside of Google. The guy who found the new sources in Milagro now has his own company on data science. And, you know, so we insist that they know something useful to society, whether they happen to go into academic research or not. That goes back to my advice to the students, right? This is maybe the only time in your career that you have the pleasure of doing research at the taxpayer's expense, right? But make good use of it. And, you know, so I think it's a fair deal. Because there's the other calculation I always tell them to do is, say, when was the last time you were in a classroom? How many professors were in the graduate student were in the classroom, and how many students were in the class? What does this tell you about the odds that you wind up happening to be a professor? That's why I was perfectly content believing I might spend the rest of my career writing computer programs. You know, it was okay because I learned the technical skills. I happened, by sheer luck, I mean, there's always contingencies. Oh, yes, skill, but the other people who might have gotten the job could have done the job too. So you can't count on that. I like it very much, but you can't count on it. So why do we need to measure a time to a billionth of a second? It's sort of ridiculous that you can just go and give this company in Italy, you know, a few $1,000 and they'll sell you one of these modules, right? It's available commercially. It was a spin-off from developments at the CERN laboratory, in fact. But I give you a little feel for why. Our apparatus is 150 meters wide. So let's say this is my apparatus and a shower comes down, right? So shower comes down, remember the shower front, it might sweep through the apparatus in some time, right? So that time is going to be something like 500 nanoseconds. You can even estimate that by saying light in the air travels about 1 meter in 3 nanoseconds. So 3 times 3 nanoseconds times 150 meters is 500 nanoseconds. Okay. Now we want to reconstruct that angle to within 1/10 of a degree, at least for the high energy ones. By the way, for reference, the moon is about 1/2 a degree in diameter. Now, the ratio of the whole time scale we're looking at versus precision we're doing it is 1 nanosecond in 5 out of 500, so 0.002. And if I compare that to like 1 radian, says the part of the sky we're looking at, to within 1/10 of a degree, that's about the same ratio. So we actually need that nanosecond to do the reconstruction to the accuracy which we do. And in fact, we're not limited just by the electronics. We're limited by all the effects inside the outer phototube, but that's the scale at which you have to do things if you're going to have a reasonable reconstruction of the angle. I'll just mention a little bit about data storage. We read all the raw data out of that electronics all the time. That's about 0.5 gigabyte per second into our computer farm. The trigger software, selecting which ones are worthwhile, looking for the 30 hits in 30 nanoseconds. That happens at 25,000 a second. We process it in near real time. We write to disk about 24 megabytes per second, which turns out to be 2 terabytes a day. So, you know, if you spend enough money for your laptop, you might have a 2 terabyte SSD, and we'd fill that up once a day. So we don't do it on laptops. We do it on portable arrays of disks. The data is moved by those portable disk arrays to the big university in Mexico City. So I think, see, how many students are at Hope? 2,500? 20? Okay, let's say 3,000, right? MSU, 50,000 or so. UNAM, about 100,000. And they're also quite happy to remind you that just as Harvard was founded in the United States to train preachers, right? UNAM was founded to train priests, but in 1519. So they look down a little bit at their younger brother in Harvard. And that data is moved to Mexico. And so one of the other little sociological facts, for a long time, we could not afford internet from the town to Mexico City. The internet in Mexico, to first approximation, the commercial internet is owned by a guy named Carlos Slim, who at one fairly recent time was considerably wealthier than Warren Buffett. And so he was able to charge what he wanted to. We've finally gotten things a little bit better. But it's still, the bandwidth is not enough for us to ship our data to Mexico City. So we wait, fill up an array of disks, and we drive them to Mexico City. The bandwidth is much better. Now, on the other hand, it goes from Mexico City to Maryland, and there the internet is good enough between the center of Mexico to in the U.S. We store a copy each place, and a petabyte is a 10 to the 15th bytes. A megabytes 10 to the 6th, terabytes 10 to the 12th. Yeah, there's a lot of data. And the LHC experiments have more data than we do, but this is not a small amount of data. And in all, we have about 8 million petabytes of storage at Maryland. That includes data, but it also includes simulated data, because we make fake events where we know the answer, right? In order to test our reconstruction algorithms, in order to parameterize the behavior of our apparatus, so we can correct for it when we're doing analyses, in order to simulate what cosmic sources might look like in our detector. So we have to make fake events, we have real events. And yes, we're pretty good at making sure we're not analyzing fake events when we think we're analyzing real events. Okay, I think I'm going to stop here. I'm going to talk about the reconstruction of showers next time, but there's time for a few more questions.
I have 3 questions.
All right, I'm ready.
All right. The first one has to do with the water.
Yeah.
So you truck water in and it has impurities, both chemical and also biological.
Yeah.
So what processes do you use to purify the water and what is the ultimate standard?
Okay, so we're mostly interested in the optics of the ultraviolet light, right? In the valley where it's coming out of the well, we set up a purification, a water softening plant, right? So the standards are the thing that you might have in your basement of salt and so on. It's a messy process, but okay, it's taking down in the valley, not up in the house. So we pipe up, now we truck up softened water. Inside of the purification station, we run it through a series of smaller and smaller carbon filters, okay, which remove most of the particulate materials. We failed when we tried to purify out the coloring of spring water contaminated by lichens, which are nice and orange, which is a really bad color if you wanted purple and violet, ultraviolet light to go through. So we stopped using that. And we also, I think even before, probably even before the carbon filters, we run it through a big UV lamp to kill anything biological, right? And the standard, well, so we remeasure the water regularly, but the standard is that the length of which a UV light could go without scattering or being absorbed is maybe 4 or 5 meters, so the height of the water column. So it's so that they are relatively unimpeded.
I understand why. Okay.
Yeah.
The next questions all have to do with the photomultiplier tubes.
Yeah.
How do the outriggers differ from the other ones? And you may touch on this next week, and that's okay. We can defer.
That's fine.
And also, in the same breath, what other near high energy events might be detected that would confound the issue?
Okay. So the purpose of the outriggers is dealing with really big showers. So if the shower is so big that it's larger than an apparatus, our apparatus size was sized so that 100 TeV shower could land from a photon, could land fairly comfortably on the apparatus, okay? And we could see the boundaries of it, if you will, right? On the other hand, from cosmic rays, there's many more of them. So they might fake something that looks like a photon. And it's another piece of detection to say, is it too big? Because the cosmic ray showers tend to be a little broader, right? And so if we have more detectors on the outside, although at lower density, because you can't afford to put them at the same density, it can tell you, oh, wait, that actually that lump that you saw in the main apparatus wasn't the whole shower. And therefore, it's probably not a photon. Right? So I'll talk certainly some more about that. And the other difference is that the outriggers only have one tube in them. I think it's pointing down instead of up, but I can't really remember. So it's not intended to have the same precision of energy measurement, but it is trying to say how big is the shower physically and give us a hint about whether it's poorly centered on our apparatus. And that's a hint for doing the reconstruction.
You may have answered this when I was thinking about something else you'd said previously. How many discrete gamma ray sources have you identified with high confidence at this point?
Well, for HAWC, the number is probably like somewhere around 80. For the entire field, the number is 275. We have recently gone through a huge effort to upgrade our reconstruction software. And so we're preparing another new catalog, and I don't know yet how many more new ones we're going to see. Right? Yeah.
Since we're out of time, I think I'll just call time and let's thank Jim, and I'll see you all next week.